Alrighty, so let's take a look at this. I'd like you to make sure that you have your sheet out in front of you as we're looking through this. All right, so for this first example, we have inverse Laplace transform of this big sum. So this is going to be the inverse Laplace transform of each of these pieces. Okay. Okay, inverse Laplace transform of 1 over s. We know that guy, that is just equal to 1. If we look at inverse Laplace transform of 2 over s squared, so this is just a bare s squared with no sum. This has the same format as this inverse Laplace transform of n factorial over s to the n plus 1. Where here n equals 1. So this looks like 1 factorial over s to the 1 plus 1. This inverse Laplace transform is going to be equal to t to the 1. So this term we can just bring this 2 out front. This is 2 inverse Laplace transform of 1 over s squared, which is going to give us t. Okay. All right, now this final one, the inverse Laplace transform of 1 over 5s minus 2. Okay, so power of s that we see is 1. So this should kind of remind you of that exponential, the inverse Laplace transform of 1 over s minus a is e to the at. The only difference is that the coefficient in front of the s is a 5 instead of the 1 that it needs to be. So all we're going to do here is just factor out 1/5 throughout. Okay, so I'm just going to rewrite this. So we have 1 plus 2t plus, I'm going to factor out a 1/5. Okay, so this gives me 1 over s minus 2/5. And I think we are ready to take the inverse Laplace transform of this. Okay, we get 1 plus 2t plus 1/5 e to the 2/5 t. Nice. All right. Sometimes, especially when we see squares in the denominator, we may have multiple rules called on. So I'd like you to take a moment. I've made just a slight adjustment to the problem that's in your packet. So if you can update that. Okay. And so we are going to be using linearity here. 1 over s plus 1, that's the same thing as 1 over s minus -1. Okay. And then we're going to be subtracting off the inverse Laplace transform of this piece. So we have s minus 5 over s squared plus 3. Okay. All right. So first off, let's think about matching. Let's see, this first expression is not too bad. This has the format of the exponential. So here a equals -1. And so we have e to the negative t. Then we're going to be subtracting off. Okay. Now for this next term, first take a look at the denominator. So we see s squared plus 3. And then take a look at the numerator. We have s minus 5. All right, and if we try and think about how this matches up, if we had s squared if we had just s, it would be a cosine. If we had just a constant, it would be a sine. But since we have a difference here, what we're going to do is actually just break this sum in the numerator up. Because we're able to. We can break this up as the inverse Laplace transform of s over s squared plus 3. So we, together, we didn't recognize these pieces, but then if we separate them out, they look a little bit more tractable. So we have s over s squared plus 3, and then 5 over s squared plus 3. So in our case, so we're matching the inverse Laplace transform of s squared plus k squared, s over s squared plus k squared is going to be equal to cosine of kt. So here k is equal, k squared equals 3, so k equals square root of 3. And then the inverse Laplace transform of k over s squared plus k squared is sine of kt. Okay. All right. So this gives us e to the negative t from the first term minus cosine of square root of 3t. And then, so what's going on here? Up top, for the sine term, we want to see a square root of 3. But we've got a 5, unfortunately. So I'm going to just pull out the 5, add, like multiply in that square root of 3 I want on top. But I don't want to change the value of my expression, so I'm also going to divide by square root of 3. Okay, and so that gives us sine of square root of 3t. So plus 5 over square root of 3 times sine of square root of 3t. Great. Okay. One last one, and then we'll put these pieces together.